So what we're going to look at now is a particular case where limits don't exist. So in all of the examples we're going to be looking at, the limit is not going to exist, but we can describe a little better how that limit doesn't exist. So let's look at this function right here, the graph of 1 over x squared. Hopefully somewhere somebody showed this to you once. Okay, you should be able to come up with its graph given just a little bit of time. Okay, if I plug in a 1 into this function, it spits out a 1, right? So it goes through the order pair 1, 1. And if I plug in a negative 1, it also spits out a 1, correct? Now, as I plug in large numbers for x, like 10 or 100, 1 divided by 10 squared, or 1 divided by 100 squared, these numbers tend towards 0. Okay? So away from 1, these numbers tend asymptotically towards 0. And away from negative 1, they tend asymptotically towards 0. What if I plug in small numbers? Well, 1 divided by a small number squared is a what? A big number, right? So if I did, for example, 0.1 and squared it, I'd have 0.01. And 1 divided by 0.01 is 10. Is it? 0.01 is 100. Okay? It's getting big real fast. Okay? So, in fact, this is what this function looks like as we approach 0. Does the limit exist as we approach 0? Are we approaching some fixed y value as we get closer and closer to 0? No. So the limit does not exist. And this is an important takeaway point, that the limit as x approaches 0 of f of x does not exist. We'd still like to describe what's happening. What I'd like to say is the limit as x approaches 0, in fact, let's say it like this. I want to say as x approaches 0, f of x gets large. I'd like to say that. Is that true? I mean, it appears to be true from this graph, right? So that's the idea that I want to convey, but I want to be able to give a symbol for that. So how are we going to write this? The limit as x approaches 0 of f of x, and I'm going to write equals infinity. And I want to say that this is a misleading idea. We're going to denote it this way. This is how all math people are going to write it, but it's a little bit misleading. Because does this limit exist? No. Is infinity a range value that you ever get to? It's not on the y-axis. Okay, so this is a misleading idea. But it conveys this sentence right here, which is very similar to the sentences that we were conveying in section 2.2 when we came up with this limit notation. So that's why we write it using the same notation. Okay? So the way I want you to think about it is when you see something like this, as x approaches 0, as my domain values get close to 0, what do my y values do? They get arbitrarily large. Okay? And so, in fact, let me just insert that word, arbitrarily large. Because what is large, right? Is a mile large? I don't know, right? But arbitrarily large, regardless of context, this gets large. So we're just going to summarize that. Let f of x be defined on some open interval containing a, except for possibly a itself. Then if the values of f become arbitrarily large, as x gets closer and closer to a, we write that expression there. The limit as x approaches a of f of x equals infinity. Likewise, if at the f of x values, the range values become arbitrarily, and here I'm not really sure how I want to say this, I'll say large negative. Meaning they're negative, and then in the absolute value sense, they keep getting bigger and bigger. Okay? Then we would write the limit as x approaches a of f of x equals minus infinity.